Good morning, everyone. I'm Lonnie, PhD student from UCSD. Today I'm going to talk about circuit switching under the radar with REACToR. This is joint work with a bunch of my colleagues at UCSD. We all know that data centers are important, and when services in data centers becomes more powerful with more cores, faster buses, and storages, data center networks inevitably need to move from 1G to 10G and from 10G to 40G or even 100G. So our question is how to build next generation 100G data center networks. Well, it depends on what kind of demand you need to serve on data centers. Well, studies show that data center network traffic is often skewed. By skewed, I mean if you look at one end host in a data center, look at all the flows it is transmitting to all different destinations, sort them by the bandwidth required by these flows, you get statistically, you get a distribution like this, where on the left side, you have several big flows that contribute most of the traffic. These are bandwidth-hungry flows that can easily eat up 100G bandwidth. And on the right side, you have many small flows that form the long tail. So to serve this highly skewed data center workload, one way to do is to use a 10G factory. Well, it simply cannot deliver the bandwidth required by the big flows. Another way, so to extend it, we can use a 100G factory. This is good. It provides full bisectional bandwidth. However, it is very expensive. At such data rate, most of the cables need to be optics, and it requires a lot of transceivers, which costs a lot of money and also consumes a lot of energy. So proposed in SIGCOMM 2010 by Helios and See-Through, they propose a hybrid network that works on top of 10G electrical factory with like some optical circuit links for the hotspot links in the data center. And these are switches that use these mirrors to transmit, to reflect the optical signals. And these mirrors can reconfigure in 10 milliseconds. This is good. This covers the two extremes of the demand distribution. So the next question is, how can we cover more? One way to extend this design is like what we did in what is did in OSA NSDI 2012, just by adding more circuits. This serves the aggregation demand on the aggregation level with more circuit links. Well, it is still limited by the number of circuits. So an alternative way to do is use faster switching, like we present like the modular switch we presented in last year's SIGCOMM. Modular switch, different from previous optical circuit switching, modular switch can reconfigure in 15 microseconds. This fast switching enables TDMA, where now multiple TCP flows can timeshare a single circuit link. This means they can transmit in a round-robin fashion. So this enables more circuit links, more big flows. However, it still has limitation. Well, a switch like modular is good for a few big flows. When you try to extend the coverage and try to cover more small flows, the link efficiency drops. This is because when you're serving a lot of small flows, reconfiguration takes a non-trivial time, and the links ends up just spending too much time on rotating mirrors rather than transmitting bits. To handle this issue, our approach is REACToR. It is by combining the optical circuit switch, 100G optical circuit switch, and the 10G electrical packet switch. Again, back to the hybrid approach, where we have two paths. Combining these two worlds, we get the best part of both. Oh, sorry. To build this, we start with a pre-existing 10G network, where here we have the Tor box and the end host connected to a 10G electrical packet fabric. We upgrade the end host to 100G and replace the Tor with our REACToR. At the same time, we multiplex the link to our new 100G optical circuit fabric, where REACToR here will schedule all the small flows to the 10G electrical path and the big flows to the 100G circuit path. The challenging part of this is these two networks work in inherently different ways. Where the electrical path, it has lower bandwidth, but it has buffers all the way, so the packets can transmit at any time. For the optical circuit path, it has high bandwidth. However, it is a bufferless TDMA network, so packets can only transmit when the right circuit is connected to the right destination. So our design needs to satisfy these several requirements. First, it needs a hybrid scheduler that classifies the traffic into either circuit path or packet path. You need to buffer the packets on the end host. You need to transmit at the right time, and it also needs some rate control on the sending part. We will talk about these requirements one by one in details. First is the scheduling. For this we have a centralized scheduler that collects the demand from all the end hosts, and this scheduler will schedule all the big flows to the circuit path using a TDMA schedule, and schedule the rest, the small flows, on the packet path. For this work, in our paper, we use an Oracle scheduler that predicts the demand and builds the schedule. Once the schedules are determined, the end host now will, based on the schedule, classify the packets into different queues and map them into different hardware queues. For the packets go to the packet path, they are all mapped into one single hardware queue that can transmit at any time, but only at 10G. And for the circuit path, we have one hardware queue for each destination, and they can transmit only when the particular circuit is connected to the destination. We classify the packets on the end host NICs and buffer these packets on end host memory. Once the packets are buffered, now we need to transmit them based on the schedule, based on the circuit timing at the right time. So on the packet path, it can transmit at any time, but rate limit to 10G maximum. And on the circuit path, it can only transmit when the right circuit is connected. So we let REACToR here to pull the packets from the end host in real time. In particular, we send PFC frames to selectively unpause several hardware queues, where, for example, here you have a REACToR and an end host. You have a packet queue and two circuit queues to different destinations, where the packet queue is always unpaused, or transmitting at 10G at any time. The circuit queue can only transmit when the right circuit is connected. For example, when circuit to host A is connected, REACToR will send a PFC frame to this end host, which unpause QA. QA starts transmitting via the circuit path. And we want to switch to another circuit path, like say host B. REACToR will first send a PFC frame to pause flow A, and flow A stops transmitting. Then we do the circuit switching, switch to host B. Then send another PFC frame, then unpauses host B, QB, and this completes the circuit switching. And note that when we unpause the flow, it is very likely that the circuit path will transmit at full line rate. However, this creates a small problem on the downlink merging path, where the multiplexer has incoming, if it also receives packets from the packet path, then it has in total 110G incoming, but only 100G to the end host. This creates a downlink merging congestion problem. Well, our way to handle this issue is to just really limit the circuit path and the transmitting part to avoid this overloading at downlink. This also avoids using a large buffer on the multiplexer. That was the design. Now I'm going to talk about the implementation. To implement this, to have the control plane work on real time, we implemented on a Vertex 6 FPGA, which has a lot of IOs and can timing precision up to 6.4 nanosecond. And we built a prototype of two reactors using two Vertex 6 FPGAs, and scale with a scale down with a 10:1 ratio scaling down. So we built a 10G 1G prototype where we have a control host computer that has takes the demand and configure the schedule to the reactor, streaming the schedule to both FPGAs, we use modular circuit switch, which we presented in last year's SIGCOMM for the circuit path, and we use a commodity electrical packet switch, but really limited to 1G for the packet path. Each reactor here supports 4 end hosts. For this implementation, our end-to-end reconfiguration time is 30 microseconds. So for that, we pick a scheduling period of 1.5 milliseconds. This means we reconfigure the schedule every 1.5 milliseconds, and this schedule will last for 1.5 milliseconds. As an example, for the worst case, when this A host has an all-to-all traffic pattern, each host has 7 flows going on. We need to switch the circuits for 7 times in 1.5 milliseconds, and this gives us 86% duty cycle. To evaluate our test bed, we have 3 experiments. First experiment is to show how we support TCP. Second experiment to show how we react to time variant demands, how to react to demand changes. And the third experiment demonstrates the benefit of using our hybrid approach. The first experiment is talking about supporting TCP. This is like in data centers when we have most applications are using TCP. So if we can support TCP with high performance, then it means like it won't likely break the upper level applications. For this experiment, we set up a all-to-all traffic pattern where each host receives 7 TCP flows from all other hosts. We cook a hybrid schedule where we schedule all the data packets via the circuit path and all the ACK packets via the packet path. It is a 7-flow TDMA network, so each flow fair shares the link with a 1/7 ratio. And we want to check if TCP works with high throughput. And if we plot the TCP throughput at a 3-second level, it looks like this, where each flow will evenly split the throughput, in total 86%. And if this is looking at the high level. However, if we just look at a 1.5 millisecond time scale, you can see that actually it is transmitting a TDMA pattern, where each flow transmits in a round-robin fashion. And actually, to show that we can reconfigure very fast, we use different TDMA pattern for different scheduling periods. So you see the pattern is different for each 1.5 millisecond. This shows that we are ready to all kinds of demand changes. So this first experiment shows our TDMA schedule is invisible to TCP, where TCP feels like it is using feels no difference as using a electrical packet network. So our second experiment now will show that how we react to demand changes, where this one is to show if there is a sudden demand change, how reactor will react, especially when it mispredicts the demand and is using a wrong schedule. For this, we have a workload that changes from an intra-rack traffic pattern to an inter-rack traffic pattern. Before the change, each end host is receiving data packets from all the other end hosts in the same rack, and after the change, it is receiving packets from end hosts on the other rack. For this, to impose a sudden traffic pattern change at a precise time point, we use package-gen that works that runs in Linux kernel, and see if reactor can react in time. So this is the packet trace looking at end host 8, where first it receives packets from the end host on the same rack using a 3-host round robin. And when the demand changes in the middle of the scheduling period, well, the packets will continue transmitting for a while because these are packets that are already buffered on the end host. you can see that it also starts receiving packets from the other rack. These are transmitting via the packet path at 1G data rate in total. And for the next scheduling period, like 1 millisecond after, it will start receiving from the four other end hosts on the other rack in a 4-host round-robin pattern. This completes the demand change. So this experiment shows that our reactor can react fast and robust to demand changes. So the last experiment is trying to demonstrate the benefit of using a small electrical packet switch as a hybrid approach. So for this, we want a larger scale, so we use a simulator that simulates a testbed of 64 hosts. This simulator we calibrated the simulator we used against the real testbed for 8-host case, and the difference is always smaller than 1%. So for this experiment, we scheduled a workload of ranging from skewed workload to very skewed workload. In particular, for the skewed one, we have 1 big flow and 20 small flows, where the big flow contributes 50% and the other small flows contributes the rest. But for the very skewed one, we have 1 big flow that contributes 99%, and the other 21 contribute only 1%. We serve this workload on different network architectures. If this were be served on a 100G electrical factory, it will always achieve 100% in link utilization. However, remember, this is very expensive to achieve. If we serve it via a pure optical circuit switch, then the link utilization ranges from 75% to 85%. This is because it takes some time for switching to reconfigure the circuits, and also when the demand is highly skewed, it lost more due to the inefficiency of the circuit usages on the small flows. And note that data center workloads are often highly skewed, so it typically works on the region on the right. Well, this is the curve we produced by reactor, where for the skewed workload, it can achieve link utilization of 90%, and for the very skewed, it can achieve like 100%. Same to the electrical factory. This is because it spontaneously splits the demand into 2 parts, while it only needs to serve a subset of big flows on the circuit path. When it is highly skewed, it only needs to serve 1 big flow on the circuit path. So it can achieve 100%. Focus on it does not need to pay penalty on switching and focus on serving big flow. So this shows that reactor have performance akin to 100G factory. So in conclusion, by combining a 100G optical circuit switching and 10G electrical packet switching, we have a hybrid architecture reactor that can deliver performance akin to 100G electrical packet switching for typical data center workloads, but with a much lower cost. Thank you.
So yeah, we can take a few questions. So please come up to the microphones and then share interesting thoughts or questions. So while waiting for some questions to happen, so I have one question then. So the entire benefit of this system seems to be dependent on how precisely and quickly you can estimate the traffic demand, especially between the TORs. So, and that seems to be a very deep problem in itself. And could you share your thoughts and experiences around that problem?
Yeah, well, this is actually, the demand estimation part is actually ongoing work in our group and for the reactor. Currently, our approach is trying to monitor. First, we can take soft hints from the application layer, and also we have a library that can monitor the queue depth on all the end hosts. But we are still working on it.
Okay.
Right.
Did you actually have a separate paper talking about that NIC level queue based demand prediction or something like that? Or it seems like I have seen some.
Yeah, we have another paper for we have another paper like on the third day, which is on the but that is on the NIC queuing part. But it is not about demand estimation. It is more about rate limiting.
Okay.
Right. So I think demand estimation is more like future work.
Okay.
Yeah.
Great. Thanks. Any other questions? I mean, I don't mean to monopolize these Q&A sessions, but I can keep asking.
Yeah, I was
yes?
curious about your experimental hardware. So you're not actually, you're just emulating this. You're not actually using mirrors to do optical switching.
We are.
Really?
We are using the modular circuit switch, which we presented in last year's sitcom. It is a real optical circuit switch.
So those are on those daughter boards sitting off the main FPGA board, or?
No, it is actually sitting on another rack beside our FPGA.
Okay, so it wasn't shown in the picture. That's what I was wondering. How is that actually working? I couldn't imagine it. That's why I was asking this question. So there's actually some other piece of hardware we can't see where you're actually flipping mirrors, literally.
Right. And the FPGA will send the control signals via I/O pin to these circuit switches.
Fascinating. Thank you very much.
Great paper. I was wondering about the diameter of the network because since there's no buffers, every node has to agree on what the circuit is to complete it before you can start using it. So any estimates on how big you can make this network, number of nodes, diameter? In order to make all of the circuits to be complete before you start using them and change them every 1,500 milliseconds.
Yeah. So for the prototype, this is only for our prototype. Our implementation prototype only has 8 hosts. So I think the timing parameters and the scale is not like a big problem. However, like scaling it up, which is very challenging. For example, for 1,000 hosts and even 1 million hosts in a real data center. And I think this is also like future work for us. Right. Thank you.
Can take one more question. Okay, if not, let's thank the speaker.